Hi folks, welcome back to Physics with Captain Rod. I'm making this video to help demonstrate how to incorporate frictional forces into free bodies and how to apply Newton's second law when frictional forces are relevant. So in this example, we've got this car driving along here at 60 miles an hour. And 250 feet away, a brown bear steps out into the road. And we're going to try to calculate whether or not that bear's in trouble, whether or not the driver can stop that car before he hits the bear. And we're going to assume that the roads are a little slippery. You know, really good tires would have a frictional coefficient really close to 1, but we're going to use 0.8 here. And that would occur if we had slippery roads or maybe a little dust or something on them. All right, so $1,000,000 question is, given that frictional coefficient, can that car stop in under 250 feet? So the first thing we'd probably want to do with this is take the 60 mile per hour and convert it to feet per second. The reason, well, I know the gravitational acceleration is 32 foot per second squared, and I also know that this bear's 250 feet away. I've already went ahead and did the unit conversion. If you don't know how to do unit conversion, you know, I've got videos on unit conversion. I would go review that if you don't know how I got that, because that's something you have to be able to do in physics quite a bit, is shift units from one set to another. All right. Now, as far as studying the motion of the car, the velocity graph would be a very useful thing to create here. However, before we create the graph, what we'd like to know is the acceleration of the car. That we can get from Newton's second law. So we may start with a free body diagram. And for those of you who have me in class, you know I really do not like to use the original picture for free bodies. I really believe that you should redraw the system. So what I'm going to do here is I'm going to copy this car and draw a picture of it somewhere else. All right. You should redraw what it is you're analyzing. And now I'm going to go ahead and draw force vectors on it. All right, now go ahead and use my straight edge tool as well, so I get really pretty free bodies. All right, so the first force I can think of acting on this car is the gravitational force. So I'm going to go ahead and put a force vector in for that, straight down. Oops. And label it mg. Or you can label it gravitational force or weight or something like that. Another important force. All right, we have normal forces at all 4 tires. Sometimes you have to separate those and look at them separately, like front or back tires, and other times you can just group them together. I'm going to just group them together. Those 4 normals, call them one normal force up. Now, when the driver hits the brakes, the frictional force on the car is going to be to the left. Friction always opposes motion. So our frictional force on the car is going to be this way, something like this. Now, depending on the class and how detailed the problem is, sometimes you have to break this down into front wheel friction and rear wheel friction. I'm just going to put one frictional force. I'm going to assume both tires are just locked up. And this frictional force vector is the sum of the 2 frictional force vectors on the front and rear tire. And that's pretty well the complete free body. I don't really see anything else to consider here if we throw air drag out. Now, when you're dealing with friction, you'll typically need the normal force because the frictional force is equal to the coefficient of friction times the normal. So the first thing I'm going to do here is go after the normal. Sum of all forces in the y direction equals 0. This car is not accelerating up or down. So we get n minus mg equals 0. So the normal is equal to mg, which is the weight of the car. Now at this point, you might be thinking, but the weight of the car, the mass of the car is not giving, and that's correct. When you hit a variable and you look, it's not there, just give it a name and move on. So basically m is the mass of the car, now I'm going to move on. It may or may not be needed by the time we get to the end of the problem, but don't get stopped just because you see a variable you don't have. You want to keep working and try to push the problem through. All right, next equation. Sum of all forces in the x direction equals ma. Now, my standard rule of thumb for picking a direction that's positive is this. Identify the acceleration direction, call that positive. Look at the original picture. The velocity of the car is to the right. but the velocity is decreasing. Therefore, the acceleration is to the left. So I'm going to go ahead and do left positive. And looking at my free body, there's only one force in the x direction, the frictional force. So we're going to have the frictional force equals ma. Now, the frictional force is equal to the coefficient, the coefficient of friction times the normal. And the normal from our free body is equal to mg. So what we got is that, you'll notice the mass divides out. The acceleration of the car is 0.2 g. I'm sorry, not 0.2, 0.8. It's going to be the frictional coefficient times g. In this problem, we're using 0.8. And because I'm working in units of feet and seconds, I'm going to use 32 foot per second squared for the gravitational acceleration. And I get 25.6 foot per second squared for the acceleration of the car. Oops, 25.6 foot per second per second. All right. 25.6. Okay. Not the prettiest 25.6 I've ever drawn, but good enough. All right. Now that we know the acceleration, the next step would be to do, what I call the motion study of the car. So I'm going to come over here now, and I'm going to draw a sketch. I'm going to graph what the velocity of the car against time will look like. So we got velocity against time. And what I'm going to do here is I'm going to assume the car stops. So I'm going to calculate the total stopping distance for that car. And then we'll just compare it to the 250. So, assuming the car does in fact stop, my velocity graph would look something like this. The first point on the graph, that point, 88 feet per second. The time, I do not know yet. But the final velocity, assuming the car does in fact stop, would be 0. This graph I know to be linear because I'm looking right here. This acceleration is constant. It's not a function. Okay, now as far as how does this relate to the graph? By slope. The slope of this line is the acceleration of the car, and we know that that's equal to minus 25.6 foot per second squared. And that's going to equal, delta v. That distance is my delta v, and that's minus 88 feet per second, divided by, that's my delta t, which I'm just going to call t. And now what I'm going to do is I'm going to solve this for t. So what we're going to get here is 88 divided by 25.6, and out comes 3.4 seconds. Now, I just realized a step that I kind of skipped that I'd like to go back and chat about. Right. There's really two different sets of physics taking place here. Let me kind of separate them. Right. On the left here, we got Newton's laws of motion, which I've done up positive and left positive, and I did that based on my acceleration direction. Over here on the right, what I have is a study of the motion of the car, and what I should have done, I kind of skipped it, but I'm going to go back and do it now, is before I even did the velocity graph, I should have put a coordinate system origin in this car, or in this problem somewhere. I'm going to go ahead and put one in right now. So I'm going to do this in blue. Bang. So there is my x coordinate. The y coordinate of the car is not changing, so I'm just going to use one coordinate for this problem. So that's the coordinate I'm using to track the motion of the car. So as the car moves along, once it's here, 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 its x value is getting bigger and bigger and bigger. Now, a point I want to make is you'll notice that I've got x positive to the right for the motion study, and x positive to the left for the Newton's second law problem. Yeah, you do not have to use the same set of coordinates to study the forces that you do to study the motion. And there's lots of cases where those will be different sets of coordinates. So I've inherently used a different coordinate system. Whoops, I erased it. For the motion study of the car. Let me put that back. And what I've done is I've put a 0 here, calling this way positive. Oops. Calling that way the positive x direction to study the motion of the car. Alright, so getting back, my velocity at t equals 0, 88 feet per second. When the car stops, hopefully before it hits the bear, velocity is 0. I used the fact that the slope of this line is the acceleration, which we found earlier, 25.6 foot per second squared. Now this acceleration was positive in this set of physics because I have left as positive. However, when I use that value over here, noting that my velocity is decreasing, in this set of coordinates, that would be a negative number. So that's why my acceleration over here is 25 foot per second squared with a minus sign in front of it, because the acceleration is left and I've got right positive for my motion study. Solve this for t, 3.4 seconds. Now I can get the delta x, the change in position of the car, from that area right there. 1/2 3.4 seconds times 88 feet per second. And we're going to find out if that bear's in trouble or not. 0.5 times 3.4, or maybe I should say find out if the car's in trouble. I get 150 feet out of that, basically. 150 feet. This car should be able to stop easily before it hits the bear. So I like problems like this. I like to go through problems that demonstrate, multiple types of physics in the same problem. In this problem, we have a Newton's second law application and using a velocity graph to calculate the displacement of the car while it was slowing down. I hope that this was successful demonstrating these concepts. Have a great day.